All right, so I'm just going to play the repeat game. So we're tying everything together for proportional relationships, talking about it verbal, equation, table, and graph, how they all fit together. And so if it's talking about the student council selling t-shirts and it says each t-shirt will donate $5, then we kind of can already go to what our equation is, which is y equals 5x. But if we didn't see it that way, we can flow from any direction, including go right to table. If they sell no shirts, then that tells us that they will make no money. If they sold 10 shirts, because they said each shirt is $5, I know I'm multiplying 10 by 5, so I know they're going to be able to donate $50. So we see that our proportional or our constant number is to multiply by 5, because if they sold 20, it'll be $100 that they'll be able to donate, and so forth. So we'll see that a constant of proportionality means that I'm able to multiply by the same number, and I'm going to get an output. Because remember, this is our input, this is our output. So our y is our y is always our output. Our x is always our input. So our money will constantly keep growing. And so these are become our coordinates. So this is our coordinates for our graph. Once we have a table, we can have a coordinate. So 0, 0 is here. So I would plot 0, 0. Then 10, 50. So at 10 shirts, I can go to 50. At 20 shirts, I can go to 100. And remember, you only need a couple of dots to be able to connect the dots to know that you're going to just keep going. And it should be proportional because it goes through 0, 0. Because these are the number of shirts. Wait, shirts. And this is the money for the donations. So now when we are looking at it and looking at the questions, it says, describe how you know that the above situation is proportional. Well, there are multiple ways that we can know this is a proportional situation. Can someone share how do we know that this is proportional? Yes, Alex. Right. So the graph goes through origin. Is there anything else that lets us know that this is a proportional situation? What about in the equation? What have we noticed about all equations that are proportional? Anyone? Okay, so what another way that I know it's proportional is that it also, when I know that I can do y over x, and I'm going to get the same number over and over again. So my y over x being 5 every time, and that it's a constant. That's how I know that it's proportional, because it's constantly staying the same. So find the constant of proportionality. Well, we kind of know that from the equation. Or we can use any of the forms, but we know y over x. So if I use anything even from the table here, so for example, if I use 10 and 50, that'll be 50 over 10 will be 5. What does the rate of change represent in this situation? That $5, simply that for, well, let me say that for every $5, for every $5, wait, what is it? For every 10 shirts sold, we donate $5. No, for every shirt sold, wait, for every $5, one shirt is sold. Well, I'll say it like that. One shirt is sold. Let me take a sip of water. So for every $5, one shirt is sold. That's another way we can tell that it's proportional, because it's only one thing happening, and if they sell nothing, they make nothing. What does the order pair 1050 represent? It represents that if 10 shirts are sold $50 will be donated. Again, all we're doing is taking the very words that's related to the table, graph, and verbal to be able to say what the situation represents. If the student council sells 80 t-shirts, how much will they donate to the animal shelter? So I can use our equation, y equals 5x. And if I was to say that 50 t-shirts, I know this is my x, because this is the amount of shirts that they sell. So I can say y will equal 5 times 80. And when I multiply 5 times 80, I'll get that my y will be $400. And that's truly all the tying together for proportional relations are. I'm going to go to the next page. So here's another scenario where you don't have the verbal, but the only thing they give you is how many hours and the equation. So based from this equation, what do you think I need to multiply every hour by? By 3. And so when we do that, so then we can just constantly keep building what we need to build a graph as well as do the verbal description. So that's 3, 6, 9, 12, 15, 18, 21. And then when you go to graph, you use 1 and 3. So 1 and 3, 2 and 6, 3 and 9, and so forth. It goes through our origin, so we know that this is proportional. Can someone come up with what we can say is a verbal description of what's happening here? Yes, Jordan. Okay, but we need a scenario. So we need a verbal description of what does this mean? What's happening? Yes, sir. Okay. So is it talking about harvesting pumpkins, or what are they talking about with pumpkins? If we look at the graph, I mean, because on the graph, it tells us a little bit more. It says the number of pumpkins painted. So what can we say? You can use the very thing, but let's not use harvest. So you said for each hour, 3 pumpkins are painted. That's truly it. It's. I will go over the last example as well, just so that we can make sure everyone kind of sees how it all flows together. But again, proportional isn't very complicated. It's just truly meant to show us that how if we have a proportional situation, we can do great things. All right. So here, this time they gave us a table that's not fully filled in. So we do have to rely on the fact that we do y over x to ensure that we know what's happening. So we know this will be our y because miles is usually always over time. So y over x based on what I already have here. So I'm saying 9 over 6, and I need to simplify that. So I know 6 can go in there one time, and that leaves with 3 and 30. So that's what, 1.5? And so I know it's 1.5. But remember, if I need to make sure, well, we already know this is going to be a proportional table, but in situations where we're not sure, we still have to do y over x twice. You need to do it at least 2 times to make sure that it's proportional. So if I got 1.5, I need to make sure I get that again. So 18, so 12 going into 18 is also 1.5. So now that I know that, I can multiply this by 1.5, this by 1.5, and I should still be able to get the answer. So 3, 6, 9, 12, 15 will be what fills in my table. So what will my equation be? Santiago, what would our equation be if our constant rate is 1.5? Thank you. Y equals 1.5x. So we have our equation. So if we look here at the graph, so we know that at 2 hours, he did 3. So at 2 hours, I go to 3. At 4 hours, he was at 6. At 6 hours, he was at 9. Can someone give us a verbal description? We have to use hours, miles traveled, and we're talking about a Jaguar. So what can we say about the Jaguar? Amari, can you help us out with that? What can we say about the Jaguar? If we already know that our constant rate is 1.5, we know that how he traveled based on our table, what can we say as a verbal description relating to the Jaguar? You said that the Jaguar did what? I repeat. Okay. So the Jaguar moved 1.5 miles each hour. Great job. All right. So that's really it.